What is going on, everybody? Welcome to part 8 of the Pytorch tutorials. In this video, what we're going to be talking about is model analysis, or I guess like basic model analysis. So the topic of figuring out how a model works and why and how good it is a huge research question. But for the most part, for most of the tasks that you're going to do, at least for me personally, I would say these two metrics, or really four metrics, account for 99% of the time, or account for what I need 99% of the time, and that is the in and out of sample accuracy and loss. So in sample accuracy, in sample loss, out of sample accuracy, out of sample loss. With those four values tracked and trended over time, you can pretty well tell, at least for our purposes, what we're after is either two things. How long should we train a model for? So at what point should we stop training and, hey, this is all we're going to get from this model? As well as what model is better. So how do we determine, like if we want to compare two models trying to solve the same task, which one is better than the other one? So that's what we're going to get into today. So in order to do that, basically all the code is the same as it's been up to this point. The only thing I've done is I've gotten rid of our train and test function. I'm going to end up kind of remaking those here. And the reason why I want to do that is before, you know, this whole series, and anytime we're doing something complicated like deep learning, my job as a teacher is to simplify, 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 but at some point we start violating certain rules like don't repeat yourself. So really what we want is some sort of function that accepts data that we pass and returns outputs, right? And also, if necessary, calculates gradient and loss and all that. So the first thing I want to do is actually create a forward pass function, because really what we want to do is, while we are training, we also want to do tests. We don't want to just do a test at the very end. And then also, we don't necessarily even want to just do tests like every epoch. We'd like to do pretty granular testing. We don't necessarily want to do a test every step or for every batch. But if we want to, we'd like the ability to. So anyways, the first thing I want to do is make a new function, and I'm going to call this forward pass. I can't think of a better name for it right now, so I'm going to go with that. Obviously, pass is taken. Fit is not quite accurate because we're not going to use this just to fit. We're going to use this to also test. So not fit. So anyway, this is going to take X's, Y's, and then it'll have a train flag that we're going to default to false. So when we pass data through here, by default, we will not update weights. We'd rather that be the case because, again, it is so easy to cheat with neural networks, you know, unintentionally. And so if you set the default to be true, you might forget, and it's going to train on your validation data. No good. You might not realize that's happening. Whereas if you forget to set train equals true, your model's not going to learn, and you're gonna find out really quickly something's wrong. So anyway, little stuff like that, as small as it is, it really will make a difference. You'll make so many mistakes, especially with Pytorch. Like, Pytorch is really cool. I think it's great for learning. And it's really cool to do custom things with Pytorch, and I'm still kind of undecided on which I like better, like Pytorch or TensorFlow with Keras, but it reminds me of working with raw TensorFlow in the sense that you can make a lot of mistakes and get lost very fast. So anyway, little stuff like that you've got to always be thinking about. So anyway, moving on. If train is true, we're going to go ahead and net.0grad, so we'll zero the gradients. I'm not going to handle the torch with, was it torch.nograd or whatever. I think we'll try to call that. I think we can get away with just calling it before this function. That way we don't need to use, because otherwise it'd be hard. But anyway, moving on. We're going to say outputs equals net x, so we'll just pass whatever that x is. And then regardless of whether this is an in sample or out of sample, either way, we want to be calculating accuracy, because we do want both in and out of sample accuracy, because one of the main things is comparing the two. Most of the time, your in sample accuracy will be greater than your out of sample accuracy. There are going to be times where you've messed up somehow, where your out of sample accuracy could in theory be higher than your in sample accuracy, but usually that's a major red flag. So outputs net x. Okay, so what we need to do is first we want to know how accurate we're. So basically we want to compare y in outputs. And in any case where the argmax of y is the argmax of output, right, as we iterate over this, because this will be a batch of data. So basically it's how many argmaxes are identical to each other, and that would be how much you got right. So whether this is an out-of-sample test or an in-sample test doesn't really matter. We want to know how many are identical. So we're going to say matches equals, and we're going to say the torch.argmax I, and then we're going to assert that it's equal to the torch.argmax of j for I comma j in zip, and we're going to zip together outputs and y. So I'm assuming people at this point are pretty familiar with Python, but it's just a nice little tight list comprehension. But for I, j, and zip, we're just combining them together. Outputs and y, we're just comparing the argmax of both of those vectors, and as long as those are the same, this will be true. If they're not the same, it will be false. So then all we want to do is we want to count how many true and how many false. So we're going to say accuracy, or accuracy, equals matches.count, and we want to count how many trues do we have, and then we'll just divide it by the len, maybe, the len of matches. So how many true matches over the length of matches, so this will give us a percentage accuracy. Then we're going to compute the loss, and that's going to be loss equals loss function for outputs y, and I do believe we should have the loss function. Did I zoom by it maybe? Yes, there it is. Okay, cool. So we already have that defined. So, okay, so we've computed the loss, and then finally again we're going to ask one more time if train. We want to loss.backward. We just basically do our back propagation, and then optimizer.step. Cool. And then we will return the accuracy and loss. So now we've got this forward pass function, and this we're going to use this both for training and testing purposes. So for example, we can create a test function now. We can say how much do we want to test, and so we'll just say for now we'll just default to 32. X, y equals test x up to the size, and then test y, slice that size. Sorry, I'm still trying to decide on a decent way to get a random slice. And part of me is thinking that one way I could do it, I just thought of a way I could get a random slice. I've been trying to determine how to get a random slice, because what I would normally want to do is normally I would just zip these two things together, convert it to a list, because you can't shuffle a zip object. And then slice it, and then put it back out. But then I was getting all kinds of torch and tensor issues doing that. It was super messy. But now, just now, unfortunately, I hate when this happens, because then I want to try it live, and it's usually a mistake to try things live. But what if we could say random, let's say a random start point is equal to, I think we have NumPy already here. NumPy. So what if we just said NP is, oh shoot, I can't remember now too, is NP rand, oh, I could actually do this on a different cell. Let me just pop down a cell here real quick. Import NumPy as NP, np.random.random. Okay, so that's gonna be a random number between 0 and 1, and really what I want is a rand range. Random.rand range? I don't think, yeah, you don't do that for me, huh? Urgh. Is there a rand range? NumPy rand range. Random sampling. NumPy.random.rand int. Can I specify rand int? Takes at least, how about rand int to 100? Can you do that? Okay, so it goes from 0 to 100, it looks like. Okay, so what I'm thinking we could do is we could take size. So if like size equals 32, we could say rand int, and then we know what the len of test x is. So it should be anything from 0 to the len of test x minus, jerk, don't do that to me, size. Cool. Oh, I'm kind of proud of that. That'll work. There's probably a way better way than this, but hey, check it out. So now what we can do is that, so we get a random start, and now instead what we'll do is we'll slice random start to random start plus size. So this just always leaves room for whatever that size is, and then we slice from that random size to size, and now we should get a random slice. It's not a random, it will just be a slice starting at a random point, so it's not going to be like shuffled or anything like that, but that'll be good. That'll give us a better distribution of validation over time. So cool, we're going to go with that. Hope that works. Okay, so val ac and then val loss will be equal to forward underscore pass and x, y. So yeah, we'll pass x, y, and train will be false, correct? We've defined, yes. Okay. So, oh, and then we also need to view this. So dot view as a -1, 1, 50, 50. And then x dot view, and then dot to the device, and then we need to do y dot to device, y dot to device. One option we do have too is we could actually take in any x, y, and then put it to the device in the forward pass. I think that might make things look a little better, but and then we wouldn't have to code the to device nonsense every single freaking time. I'm gonna carry on. I've already made too many, too much change. I can't wait to see if that works. Okay, so we've got val ac, val loss, and then we need to return val ac, val loss, and okay, I think we've got a valid test here. Let's go ahead and run one real quick. Val ac, val loss equals test size equals 32. We'll go with that. That's fine. And then print val ac, val loss. Also, ooh, I'm gonna make one more change, I think. Random start. So right here, I think, with torch.noGrad. Do that. I think we can get away with calculating the gradient. If I remember, this video is probably gonna be really long. I apologize. Although anybody still at this, you're probably interested in this topic, so fine. I think that'll be good enough, so we're not wasting time calculating the gradients. We definitely don't want to calculate the gradient, or do we? Actually, I don't think we can do that. We'd have to calculate the gradient so we can. No, I don't. We'll run this way. Let's run this really quickly. Okay, so we get the validation accuracy is 56, and then our loss is 0.24. That should be good enough. So cool. All right, let's run that one more time. Wow. And that makes sense that it's varying because we're taking a random slice. So that's kind of exciting. And then hopefully as things train, we'll get a little more consistent validation accuracy. So, because I bet if we did like 1,000, although is that going to batch 1,000? My GPU can probably handle it though. So yeah, if we do a very large batch, you see it does trend towards 50%. Okay, so moving along, we're ready to actually start the training loop. So we're going to basically, in the train loop, we're going to just call test as frequently as we want. Now, there's a couple things we're going to think about here. Is in our train loop, basically we want to train the model. But as we train the model, we also want to track how is the in-sample validation, the in-sample accuracy and loss comparing to out-of-sample accuracy and loss. So we want to be logging that information, and then we'd like to visualize it. Like you could just output it to a console and look at it, but it's pretty useful to like visualize it on a chart, like a graph. Now I know people, if I don't bring this up, people are going to be like, "What about?" And that is TensorBoard, which is the visualization module that comes with TensorFlow. But you can install TensorBoard, and then apparently you can use something called TensorBoard X. With Pytorch, and that should allow you to use TensorBoard. I don't know. What I do know is what I use TensorBoard for is to just graph some scalars. Okay, that's basically it. So I'm a little confused why anybody is going to go way out of their way to use TensorBoard when you can just graph it in Matplotlib. So again, 99% of what I'm doing with visualizing, and analyzing a model is I'm graphing the accuracies and losses. And actually, what I'd really like to be able to do is graph them on the same graph. And with like TensorBoard, I can't even do a basic thing like that without seriously customizing TensorBoard. It's going to take more code. It's going to take more understanding of like TensorBoard and stuff like that. Whereas with Matplotlib, like I can have any graph I want. If I want to graph some scalars, cool. If I want to graph some bar charts, cool. Also, it's Pytorch. You don't have to use Matplotlib. You could use Plotly or like Dash. You could make your own TensorBoard. You could make, you could go with like PyGal. You could do anything. You could graph with some other JavaScript plotting library. I think the whole reason anyone's going to use Pytorch is for custom stuff. So it just seems wrong to use TensorBoard. It's not, I mean, I use TensorBoard with TensorFlow because the code's already all done for us. But what I don't understand is why someone would use Pytorch and then like basically port Pytorch to TensorBoard. I'm just not on board with that. I know some people might want that. Just understand that TensorBoard X is probably where you should start looking. Okay, so that's what we're going to do. So in order to do that, we need a little silly log file. So to have a log file, first we're going to want to save the model name to the log file so we know what we're graphing. So for a model name, generally I would give it a nice name of something to do with the type of model you're working with. So is it a 3-layer, 64 feature per layer conv net, stuff like that. I would try to make a useful name. For now, I'm just going to say model dash, and then we'll go with int time.time. So I've always, no matter what I name the model, I've always appended time.time to my model names just because eventually you're going to change something, you're going to forget to change your model name, and then whether you're using TensorBoard or what we're doing here, your data is going to run over each other because you're using the same name, and you're really going to kick yourself for it. Whereas if you just do this every time you run the model or make a new model, it's going to have a new time. So you're welcome. That will save you. It has saved me so many times. So now what we're going to say is net equals, and we're just going to start with a new one. So net.to device, and then we will redefine our optimizer and loss function, blah, 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 come down here, cool. Now, let's go ahead and print model name just so we see it and know what we're doing. And then now we're going to define a train function. Okay, so what do we need here? First of all, we need a batch size. Go with whatever you think can fit on your GPU. I'm going to go with 100 so it goes relatively decently fast. If you're getting a memory error, go with like 16 or 8 or whatever it takes. 100 for me. Epochs, I'm going to go with 8, just some number to go with. Something, generally somewhere between 1 and 10 epochs is probably enough. But it really will depend on what kind of task you're actually doing. And then same thing too, like if you're doing like transfer learning, which we haven't talked about yet, at some point we'll probably talk about transfer learning. might even just be one epoch or 2 epochs max. But for the most part, 1 epoch is probably too few unless you have just a massive data set, which you probably don't. But at some point, you might. So anyway. All right, now we're going to create a simple log file. So I'm just going to say with open, and I'm going to call this model.log with the intention to append as f. What do we want to do? So for epoch in range epochs, and let's go with 5. For range in epoch in range epochs. Okay, what do we want to do? Well, we want to start iterating over our batches. So the way that we've done that is for I in TQDM of range starting at 0, ending at the len of train X, taking steps the size of our batch. What do we want to do? Well, we want to slice our data. So batch X equals train X. And the slice will be I to I plus the batch size dot view as a -1, 1, 50, 50. And then we're going to send that to our device. Dare I copy and pasta this? I shouldn't. I'll just write it. Okay, too many things to change, too many places to mess up. So batch Y is going to be equal to train Y, I to I plus batch size. I did that size again. Okay. And then we will send this as well, dot to device. Okay. So now we can now that we've got X and Y, we're ready to do a forward pass. So what we're going to say is ACK and loss is equal to forward pass for batch X, batch Y, and don't forget your train flag. Train equals true. Okay. So now that we've done that, our forward pass handles all of the training for us. So we actually are done with the training stuff. So now that we've got all that code up there, this is actually pretty quick to write. What is next? Well, we would like to start logging data. So the next thing we could do is do a test. So for example, val_ack val loss is equal to another forward pass of size whatever the heck you want, 100, 32, whatever, your current batch size. But here's the problem. So if you do that batch size, that means every single step you take, you're almost like double your training time because you're feeding through twice as much data. So I would propose that either one, you could go with a smaller size and do it every step, but that's not really going to be very reliable. Like you've seen already how variable a small size can be. So I'd rather go with a larger size, but do it not every step. There's really no reason to do it every step, but you know, in this for loop, do I want to do it for every I? No. But do I want to do it as infrequently as every epoch? No. So what can we do? Well, we could say for I modulo and then however many steps that you want to do it. So let's say every 50 steps we want to calculate this. So we can say I modulo 50 double equals 0. And then not 4, it should be an if. I don't know why I wrote 4 there. But if I modulo 50 equals 0, so this will be every 50 steps, this will be true. So so now every 50 steps we'll calculate val accuracy, validation loss. And then what we want to do is actually save it to that file. So the way that we're going to do that is we're going to say f.write, and then we're going to write a really long f string. So we're going to start with model name. This will be a nice little CSV file for us. So we'll start with model name, comma, and then we're going to go with round, and then we're going to round time to 3 decimals. I mean, it just kind of depends on how quickly you're doing these steps. And if anything, actually, we're going to do 50 steps quicker than a second, I think. So yeah, that's fine. That should be fine. So, shoot. This is going to get messy. We're going to hit so many errors probably. Okay, now what we want to do is we want to round the float of the accuracy to 2 decimal places. And then we're going to take this, copy, pasta, round, loss. So accuracy out to 2 decimal places makes sense. I think loss, we'd like a little more granularity, so I'm going to say to 4. Why are we converting to float, by the way? So I think with accuracy is probably just a Python value, actually. Loss, however, is going to be, where the heck are you? Here. This is going to return a tensor. So we want to get that into not being a tensor anymore. So we're just going to say float. There might be a more efficient way to do that. If you know a better way, let me know down below. And we probably don't even need to run. I don't think this actually has to be converted to a float. We can tinker with that later. For now, what I'm going to do is take this, copy, paste, and ACK loss. This will be val underscore ACK, and this will be val underscore loss. Also, I'm going to make my text a little bigger. I just realized it's pretty small. Increase code font size. In case you can't see something, you can always go to the text-based version of this tutorial. There are links in the description to that kind of stuff every single time. If it's not there, remind me. I'll put it there. Okay, so this is that whole line that we're going to write, and then, don't forget, a new line. Otherwise, we're going to be so sad. Okay, so, I think we're good. So now that we've done that, we can say, we can run train, and let's see how many errors we've hit. That's disgusting. Forward pass got an unexpected forward pass. Oh, side. We didn't want forward pass. We want this to be test. I hope that doesn't. Sometimes if you hit an error, it screws up. It's probably going to do it. I regret everything. It screws up the TQDM. We got it. Nice. Cool. Okay, so we are off. Looks like epochs are going to take about 25 seconds. As opposed to, I forget what they were before. Were they like 8? Well, they were 8 seconds, I think, on the Linode GPU. I actually haven't done it on this GPU, so I can't really tell you how much it's changed anything. But anyway. Okay, so how many epochs did we pick? 5. Okay, so we're going to run 5 epochs, and then this is the model name that we're going with. So now what I want to do is actually graph this. And the way that we are going to, I'm trying to decide, I don't think I really want to graph it in Jupyter Notebook. I think it would make more sense to graph this in a Sublime Text. Wonk. Yes, that looks ugly. Yeah, you see that too. Why is that so gross? Go away. And I want to do that so the actual graph pops up and we can be interactive with our graph. Cool. The other thing is I want to pull in, before I forget, I want to bring in, where are you? I'm gonna copy another model log because I've got one that I ran for many epochs that I want to show you guys. Because I don't want to run 30 epochs on video. That would be crazy. Cool. Okay, so I copied that so we don't have to wait, 15 minutes basically to run 30 epochs. Okay, so we are creating that data. So if we come over to model log here, right click that, open with Sublime, we get this. So as you can see here, you've got your, I already forgot what order we did things in. What was it? Accuracy loss, validation accuracy, validation loss. So this will be validation accuracy here. So as you can see, it starts pretty bad. As we continue along, though, you can see your validation accuracy is already up to 70%. and it's doing pretty good, but you can see even just looking at it, these are slowly starting to diverge pretty significantly. But it is hard. It's easy to cherry pick. Like, obviously, it looks like, hey, they're back together again. So it is hard to see. So now what we want to do is graph from this file. Now, there's a million ways we could graph from this file. One of the easier ways, honestly, would be to use pandas. I think we're just gonna read and separate the file though, because I don't want to get into pandas. I don't want to confuse anybody with pandas. But honestly, I would use pandas if I wasn't making a tutorial out of it. So anyway, carrying on though. So now what we want to do is graph that. So we're going to say import matplotlib.pyplot as plt, plt. Don't do that to me. And then from matplotlib, we're going to import style, and style.use, we're going to use ggplot. Now what we want to do is we want to grab the model name, and if you're still in your notebook, you could just say equals caps model name. In our case, this was the model name. Yay for printing it out. So I'll just do that. So next, once we have that, we can just make a little function or something, define create ac loss graph. And then we'll just pass the model name here, and then we're going to say the contents is equal to the open of model.log to read, and then we're going to say .read.split by new line. Cool. So that gives us our contents. Then I'm just going to say times is a list, accuracies is a list, losses is a list, val X is going to be a list, val losses is going to be, eventually, one day when it grows up, a list. So now what we're going to do is just iterate over our contents here. So we're going to say for C in contents, if model name in C, again, you might have multiple model names in this log, and we want a very specific model, not all of them. So we do want to make that check. If model name in C, what do we want to do? We're going to say the name, the model name, and then timestamp. That was that Unix time. Ac loss, val ac val loss. The other thing we should have probably added was epoch. I'll put that in the text base. I don't feel like going back for that. Equals C dot split. It would just be useful to know at what point did we epoch, because usually it's going to be at the epoch point where, well, one, you kind of want to know at what epoch am I, at what epoch did things start to go bad, because you're going to stop usually at an epoch. But sometimes you'll stop at number of steps actually too. So anyway, it would be useful to know both step count and epoch possibly. But you can also figure it out from the graph. So, whatever. Name, blah, blah, blah. Okay, so we've got our data. And then all we want to do now is we're just going to say times dot append float timestamp. Don't forget to convert everything to a float, because right now it's all string form. Float times, and then basically we're just going to go times accuracies, losses, val ac, val loss. So, times accuracies, losses, val ax, val losses. And then we append times timestamp, accuracies, ac, losses, loss, val ac, and finally, val loss. Exciting stuff, exciting stuff. Okay, and then we're going to graph. Now, for people who are truly novices with matplotlib, you can go to pythonprogramming.net, go to data analysis, and go to data visualization. There is tons of customization that you can do. with matplotlib. For example, let's just click on this one. This one might show a relatively complicated looking. Nope. That's a pretty basic looking graph. Custom fills, share X, Y, custom legends. Maybe this is the best one. Right. So you can make very complicated custom graphs with matplotlib. It doesn't have to be super ugly. It doesn't have to be super beautiful. But there's all kinds of crazy stuff that you can do. Like this is price and volume, so this has like a multiple y-axes. You can also, in this case, we've hidden the other axes. You can also plot multiple things on the same graph. You can do all kinds of custom fills and blah, 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 blah. Okay, matplotlib really, truly can have everything you need. But if you need to learn more about how we're doing matplotlib, if something I say in the next few moments doesn't make sense to you, there is an entire series here for you. I guess I could just leave this here. I'm just going to minimize it though. Okay, so we've got all of these, these lists here that we can graph. Time will be our x-axis, and then we want to graph the accuracies, losses, val-ax, val-loss. So what we're going to say is fig equals plt.figure, and this is just so we can have multiple figures. Like if you just wanted to graph like one thing, you really can just say plt.plot, and we could plot times, accuracies, and then do a plt.show, and that should work. Oh, we didn't call this. I'm like, it's not working, man. Model name. Cool. Let's try that one more time. Cool. So now you can see how in sample accuracy has improved over time. But alone, that's relatively worthless other than seeing that, wow, it's actually trending upwards. Well, I'll be. Didn't expect it. Okay. So it can be that simple, but I actually want multiple graphs. So I have to get a little more fancy than that. So first we define the figure, and then now we're going to define a couple of axes. Each axis is a graph. You can think of it that way. plt.subplot to grid. We are going to be working on a 2x1 grid, and so I'm going to do the same thing. Define axes dose. And it's a 2x1 grid. This one will start at the 0, 0 mark. This one, hey buddy. There we go. This one will start at the 1, 0 mark, but also we want to share the x-axis with axis 1. This way, as we zoom in and do kind of, as we interact with these charts, they share the same x-axis. Just a nice, convenient way to do that. Okay, so we have our axes. Now we want to plot on those axes. So we're going to say ax1 plot, and we are going to plot the times, accuracies, and then we are going to label this as ac. And then we're going to ax1.plot, and actually it's going to be very similar, so I'm just going to copy pasta times, and then we want to graph val-ax, so they'll be on the exact same chart. You'll see that in a moment. Val-ac, and that way we can very easily compare them and see as they begin to trend apart, because that is your big red flag. And then ax1.legend, and we'll set this to location 2. There's various locations. I just know location 2 will be out of the way if everything goes correctly. If it's in the way, it means things went wrong anyways, and it doesn't matter. You'll see what I mean. And then ax-dose .plot, and I kind of want to copy and paste. It's going to be a lot of editing, but let's do it. So it's ax2, 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 and then it is time. It's always times, but then here we want to say what is it? Losses, losses, yes, losses, and val losses. Right? Is that right? Val losses, yes. And then here, we want to say loss, and then val loss. Okay, so those are the things that we want to graph. We will run a plt.show. Show me the money. Okay, cool. So now you can kind of see, first of all, there's a couple of things we'd like to do right out of the gate is like smooth these graphs a bit. This does bother me, but I also want this video to be less than 5 hours long, so I can't do everything. But anyways, you can see, like, as I zoom into a specific spot, both of these graphs update at the same time. There's various things I'd like to fix, like, you know, alignments and stuff. But anyway, it's pretty cool because you can do that. You can click. So I did that by clicking on this magnifying glass. You can click on this button, kind of drag around and stuff. But for the most part, this looks pretty good. What I want to show you, so for example, you can kind of see if we applied some sort of moving average, which would be so much easier in pandas. The next time we do a chart like this, I'm just going to use pandas, but I try to keep things as simple as possible. But these look pretty tightly coupled. I mean, they are pretty close to one another, but you can see valac is at least slightly lower than accuracy, but this is all to be very, very expected. We can also see that validation loss, so this is your out-of-sample loss, is slightly higher loss. Again, that's to be expected, but everything's kind of trending together. It looks pretty good. This tells me I can keep training this model. Like, these are all kind of going together pretty well. It is when accuracy, validation accuracy, and accuracy start to diverge that we have a problem. And usually, actually, the losses will diverge before the accuracy. So if you really want to stop at the perfect point, you would watch loss instead. So what I've done is I moved a log file that contains a 30 epochs example. Where are you? Yes, model 30 epochs.log. So what I'm going to do is just to show you guys, so we don't have to wait 30 minutes. I'm gonna edit or I'm gonna read that file, and the name is this timestamp. Cool. So this will be a quick example. You can run this on your own if you'd like, but I just want to show you guys. This is 30 epochs, and it turns out this is actually, at the point where they start to diverge, it is about 8 epochs. That's why I had 8 as the initial number there. But this is 30 epochs. So as you can see, let's just make this nice and big. And by the way, if you graph in IPython Notebook, you just can't interact with the actual graph. So that's why I'm doing it here, so we can actually interact with it. Just as some basic information too on Matplotlib, generally I tend to go by about 40,000 plots or points on a graph. After about 40,000, it starts to lag. Depending on what CPU you're running, you might need to do a different number. Again, with pandas, you could just resample. So yeah, we'll use pandas later, but anyway, you can see here how accuracy continues to go up, and we've even got many batches that have a perfect 1.0, so 100% accuracy. But after about 80% accuracy, we can see that validation accuracy, while it doesn't actually get that much worse, it just stops improving. It's just never improving again. And we can see here that loss, kind of similar, it fell, but then actually it starts to trend back up. So it would probably be the case that as if we continue to train, we would probably see validation accuracy fall. And this is just a perfect example of overfitment happening. And you can see it so well because it's coming up, and then even the deviations here are getting smaller and smaller. Like this model is just learning to fit and just fit the input data. So it's just it's cool because that's what neural networks do. There's so many parameters that can be tweaked. And there's just so many variables that can be tweaked that you really can just memorize the data. So just keep that in mind as you go forward, and just remember, just watch the divergence of losses and accuracies, and usually you can peg it pretty quick. And anyway, so you'd really probably want to stop training the model around this point. That's basically the end. So I think that's all I really want to talk about for now, but yep, that's how you can analyze your models. Much ado about a pretty basic graph in my opinion, but we actually made a lot of different little itty bitty changes, and hopefully you can see now what happens when you train a model out way too long. It looks really great on your in-sample data, but on any out-of-sample real data, it has not improved. And again, if you continued, I imagine just looking at loss getting worse here, vowel loss. Because again, in-sample loss is only improving. It's only continuing to drop, and we've even got some zeros. Again, because it's learning to predict perfectly on in-sample data, which is bad. So, because we want the neural network to generalize, not memorize. Okay, so that's it. Hope you guys enjoyed. If you've got questions, comments, concerns, whatever, feel free to leave them below. If you want to support me, the channel, videos like this, click on that beautiful, beautiful blue join button. Help support me and the channel. If you click on that, you get early access to videos just like this one. Special rank in the Discord, a little logo by your name in the comments, and stuff like that. So, that's it. I will see you guys in the next video where we will be hopefully diving into some sort of project. I haven't fully decided. I've kind of tested out a few different things. It's very difficult to figure out what I want to go with for a project here. So I'm trying to keep it basic, but I'm trying to not do the same stuff I've always done. I want to do other things. So we'll see. We'll see. So I haven't decided what it is, but I'll see you in the next video where we're hopefully doing something interesting. Till next time.